Hello everybody. This video is going to be the second video of the second topic, Lewis structure. In the previous video, we discussed how we draw Lewis structure based on the formula. In this video, we're going to discuss the resonance structure and formal charge. Okay. All right. Let's take a look at this slide. Well, when you draw Lewis structures, sometimes you'll realize a molecule could have more than one valid Lewis structure. Take a look at this ozone molecule. If you draw the Lewis structures according to the procedures we discussed in the previous video, you will see that both structures are valid. Okay, if you check the octet rule for all three oxygens in both structures, all of them are happy. So if you have more than one valid Lewis structure, then how do you get the real structure of a molecule? Well, in science, the experimental evidence tells us the real structure of ozone molecule has two equivalent OO bonds. And this is confusing, right? Because in the two Lewis structures, one bond should be shorter than the other bond, because double bond is supposed to be shorter than single bond. So looks like, based on the structures here, looks like one bond, the two bonds should not be identical, but the real structure shows that they are identical. And what's going on here? Well, the thing is, when you consider the real structure of ozone molecule, you do have to consider both. In other words, when you see the real structure, you are actually seeing the mixture of the two valid Lewis structures. Okay, so sometimes we call it hybrid structure. It's a mixture of both. Okay, actually here you can see that we use a dashed line and a solid line to represent the bonding interaction between two oxygens, and that tells us that bonding interaction is actually between the double bond and a single bond. Okay, so that's how we discuss that's how we present a hybrid structure if you have more than one valid Lewis structures. Well, here this one gives you one example analogy here. Well, you have two dogs with two different breeds, and then if you mix them together, then you will get a hybrid dog. Okay, same idea here. So here now, let's define resonance structures. Two or more valid Lewis structures that together describe a bonding in a molecule. I'll highlight that together here. Just want to let you know that you have to consider all of the possible valid resonance structures when you consider the real structure of a molecule. All right. Now, formal charge. How do we define formal charge? Well, formal charge is a charge an atom would have if a bonding electron were shared equally between bonded atoms. Let me give you one example here. Hydrogen fluoride. If you draw the Lewis structure of the hydrogen fluoride, you will see that it will have three long pairs on fluoride and one single bond between hydrogen and fluorine. Well, if you draw the structure like this, okay, I want to show you the two electrons shared by those two atoms. One comes from fluorine, the other one comes from hydrogen. Okay, well, when we say that those two atoms share these two electrons, they share those two electrons unequally. In other words, because of the high electron negativity of fluorine, it likes electrons so much, it will pull the electron towards itself. Okay, so when they share these two electrons, most of the time, those two electrons will move around the fluorine instead of hydrogen. Occasionally, those two electrons will move towards the hydrogen, but most of the time, it stays with fluorine. Okay, so although those two atoms are sharing these two electrons unequally, but when we calculate the formal charge, we ignore this electron negativity difference. So later on, after we learn how we calculate the formal charge And if you do the formal charge of those two atoms, you will realize that both of them have 0 formal charge. Okay, we will see how we do the calculation in a moment. But as you can see that when we calculate formal charge, we ignore this electron negativity difference. Okay, all right. Now let's use examples to demonstrate how we consider resonance structures and formal charge. I'm using those examples we used in the previous video. Just want to be consistent. We have the formula for you to calculate formal charge. So formal charge equals to V minus N minus half of B. Well, V and B, what do they mean? V is the number of valence electrons. Okay, we've already talked about in chapter 3. And N is the number of non-bonding electrons. In other words, if you have dots, okay, around an atom in the Lewis structure, that means these are non-bonding electrons. They are not going to be involved in chemical bonds. Instead, they are just going to stay in the particular atom, not going to be shared by two atoms. Okay, so these are non-bonding electrons. Now the next one, B, bonding electrons. Those electrons involved in chemical bonds. Okay, in chemistry, we use those solid line to represent chemical bonds. Single line means single bond means 2 electrons. Okay, double bond means 4 electrons, and triple bond means 6 electrons, 3 pairs. Okay, in between 2 electrons. Between two atoms. This is the calculation equation. Now we have some rules for us to follow when we discuss formal charge. Okay, number 1 and number 2. These two will help us confirm our calculation regarding formal charge. Rule number 3 and number 4. They are going to help us identify which resonance structure is the best one or the better one. Okay, we will check those 4 rules when we talk about specific examples. Right, first example, methane molecule. Well, here this is a structure of a Lewis structure of methane molecule. 4 hydrogens interacting with carbon, central carbon atom through a single bond. Now let's calculate the formal charge of hydrogen and carbon. Hydrogen, valence electrons 1 minus non-bonding electrons. Well, you don't have any dots around hydrogen. That means the non-bonding electrons would be 0 minus half of bonding electrons. Well, for each hydrogen, it has 1 single bond. Therefore, we are going to have 2 bonding electrons for hydrogen. Remember, when you talk about these V and B, you have to be specific. Okay, they are about the numbers of the electrons for a specific atom. Okay, so you need to be very specific. Anyway, if you calculate the formal charge of hydrogen, it's going to be 0. All right, so let me label the 0 on the first hydrogen. And if you check the other 3 hydrogens, they all have the same calculation for the formal charge. Okay, so all of them will be 0. Okay, if you don't believe me, go ahead. And in chemistry, we usually label the formal charge right beside an atom. Okay, all right. This is hydrogen. How about carbon? Carbon, 4 valence electrons, group 14, remember? Now, non-bonding electrons, carbon, no dots around carbon. That means non-bonding electrons would be 0, like hydrogen. Then half of its bonding electrons, you have 4 bonds around carbon. All 4 of them are single bonds. And we mentioned that single bonds represent 2 electrons. So total for carbon, it has 8 bonding electrons. Okay, so here the calculation shows us it's also 0, formal charge. All right, now this is the formal charge of 5 members of this molecule. Now let's check rule number 1. Rule number 1, the sum of formal charge in a neutral molecule must be 0. Well, this is a neutral molecule, and you have all 5 zeros here for 5 members. Therefore, if you add them together, well, it's 0 indeed. Okay, so it shows us the rule number 1 is valid for this molecule. All right, this is a methane molecule. Now let's take a look at carbon dioxide. This is the loose structure of the carbon dioxide, and let's calculate the formal charge for this oxygen. It's going to be 6 valence electrons minus, well, non-bonding electrons. Well, you have 4 non-bonding electrons, right? 2 lone pairs. These electrons are not shared by oxygen with any other atoms, so these 4 electrons belongs to oxygen only, so they are non-bonding electrons. So this one would be 4 minus half of bonding electrons. Well, you have a double bond for this oxygen, and we know that double bond represents 4 electrons. Okay, so that's going to be 4. Okay, if you do the calculation, would be 0. We label 0 right beside the atom. Now for this carbon, we know that the valence electron would be 4 minus non-bonding electrons. For central carbon, does not have an unpaired non-bonding electron, therefore would be 0 minus half of its bonding electron. Well, you have 2 double bonds for carbon. Therefore, you have total 8 bonding electrons. Okay, so this one is also 0. Now, for the oxygen on your right side, it has exactly the same formula, the calculation formula for the first oxygen. Okay, and in order to save your time, okay, I'm just going to label the formal charge 0 right beside the oxygen. If you don't believe me, you double check. Okay, you will have the same calculation for this oxygen. So it's also 0. All right, now I want to show you another valid loose structure for carbon dioxide, and then we will use the some rules to help us understand why this structure is actually preferred. Now let me draw the structure, and you think about it. Well, carbon is still the central atom. 1 triple bond with 1 oxygen and 1 single bond with another oxygen. Okay. Now this is also a valid loose structure. If you check all 3 members, octet rules are satisfied for all 3 members. Okay, so this is also valid. Okay, but if you check the valence electrons, if you check the formal charge for the oxygen on your left side, 6 minus, well, you have 6 non-bonding electrons, okay, minus half of its bonding electrons. It has a single bond, therefore it's going to be 2. For this one, it's going to be -1. I'll label -1 right beside it, and sometimes you can use a circle to highlight the formal charge if it's non-zero. Now let's see carbon. Carbon, it's a 4 minus 0, no non-bonding electrons, minus half of its bonding electrons. Well, you have 1 single bond, 1 triple bond, so 6 plus 2, total 8 electrons. Therefore, this is 0 for formal charge. Okay. Now for the oxygen on your right, you have 6 valence electrons. Now non-bonding electrons would be 2. You can see 2 dots right here, and then minus half of its bonding electrons. You have a triple bond, 6 electrons, so multiply by 6. So therefore, this one would be +1. Let me label it +1. Okay. All right. So now let's take a look at these 2 valid resonance structures. Well, rule number 1 can still be applied 0, 0, 0, total still 0. This is a neutral molecule. For this structure, -1, 0, plus 1. So total is still, sum is still 0. So again, neutral molecule. Okay, now this is the rule number 1. Now, how do we know which one is better? Well, or are they equal to each other? Well, according to rule number 3, small or zero formal charge on individual atoms are better than larger ones. Well, you can take a look. You have 3 zeros here. You have 1 -1, 1 +1. So these zeros are smaller than the absolute value of -1 and +1. Okay, so in other words, this one has more zeros. This one has only 1 zero. And if you have a molecule with more zero formal charge, then this structure would be preferred. In other words, this resonance structure with more zeros would have a greater contribution to the real structure of the carbon dioxide. Actually, if you do experiments, you will see, okay, that both bonds in carbon dioxide actually are double bond. Okay, they are equal to each other, unlike this one here. Okay, so this is rule number 3. Let's take a look at this nitrate NO3 minus, and this is the loose structure of this ani. And remember when we draw loose structure of NO3 minus, and when we come up with the double bond, we said that it doesn't matter which oxygen share the lone pair to form a double bond, right? So that means that if you have this oxygen share one lone pair to form a double bond, how about, would that be, the same if you ask this, if you leave this oxygen alone and ask this oxygen to share one lone pair to form a double bond? Well, let's try it. So that means you have double bond right here and single bond right here and single bond right here. Okay, this is the second possible structure. And how about the double bond right here? Okay, so you would have single bonds and single bonds and six electrons, but this one would be 4. Okay, so you would have these 3 valid resonance structures for nitrate. Well, again, let's see whether we can use one of the rules or one or more of the rules. Well, this is a charged ion, right? So the rule number 1 cannot be applied on this ani, but the rule number 2 can. All right. Now, of course, before that, let's calculate the formal charge of all 4 members. This one, I'll label it right here. You have 6 minus 6 minus half of its bonding electrons. That's going to be 2. Therefore, you have -1. Okay, so I'll label -1 here. For this oxygen, it would be the same as this one. Okay, therefore, the formal charge is also -1. For this oxygen, let's do the calculation. Okay, that's going to be 6 valence electrons minus 4 dots, 4 non-bonding electrons minus half of its bonding electrons. It has a double bond, so 4 electrons. Therefore, this one would be 0. Okay, 0 for this one. Now, nitrogen, I'll write the nitrogen right here. 5 valence electrons minus non-bonding electrons. For nitrogen, there are no non-bonding electrons, therefore would be 0 minus half of its bonding electrons. You have 2 single bonds, 1 double bond, so total 8 bonding electrons. So this one would be +1. Okay, so I'll label the +1 here. All right, let's continue on the other 2. Well, if you take a look, this oxygen would be the same as this one. This oxygen would be the same as this one. Nitrogen remain as the same. Okay, right. So I'll just go ahead and label the formal charge for this structure: -1, -1, and 0. +1, -1, 0, -1. Okay. If you again, you can do the calculation and confirm my calculation for this oxygen and nitrogen. Okay. All right. Now let's take a look at the rule number 2 again. The sum of the formal charge for an ion should be equal to its charge. If you have -1, -1, +1, 0, if you add those four numbers together, the sum would be -1 and that matches with -1 charge of this ion. So that's rule number 2 can help us confirm our calculation regarding the formal charge. If you add everything together and it does not match with the charge of the ion, then something must be wrong. Okay, so you need to double check. And if you can check the other two structures, rule number 2 are also valid. It is also valid for these two structures. All right. Now, which one is the best? Or are they equal to each other? Well, rule number 3 says small or zero formal charge are preferred. If you check, they have all three structures, they have 1 0 and 1 negative, 2 negative ones and 1 positive one. Okay, so it looks like based on the number of those formal charges, they have exactly the same four numbers. Therefore, they are equal to each other. Okay, the contribution of those three structures to the real structure actually would be the same. Okay, so this is the NO3 minus. Now let's take a look at this structure. And here, this is the loose structure of this molecule. Now let's calculate the formal charge for oxygen: 6 valence electrons minus 4 dots. That means 4 non-bonding electrons. Half of its bonding electrons, it has a double bond. That tells us it's 4 bonding electrons. Therefore, it's going to be 0. Okay, 0. For sulfur, 6 valence electrons, okay, group 16, minus 2, okay, you can see the 2 dots right here, all right, minus half of its bonding electrons. You have double bond, single bond, so total would be 6. So total would be 6. All right, so this one is going to be +1. All right, +1 for sulfur. For fluorine, you have 7 valence electrons, group 17, remember? Now you have 6 dots, so 6 non-bonding electrons, minus half of its bonding electrons, 1 single bond for fluorine, so 2 electrons. Therefore, for this one, it would be 0, okay? 0 for fluorine, okay? So this is the formal charge. Again, let's see the rule number 2. If you add these 3 formal charges together, it's +1. That matches with the charge of this ion. Okay, so that is a rule number 2. Now, remember when we draw this, when we practice this ion in the previous video, we said that fluorine will never form a double bond because of its high electron negativity. So how about let's just try. Let's assume that the fluorine will form a double bond and see what's happened. Okay, so sulfur with double bond, okay, with fluorine, and single bond with oxygen. Okay, and it's a charged ion. Okay, now let's calculate the formal charge. This one, 6 minus half of 2, that is going to be -1. So -1 formal charge. Sulfur would be the same as this one, okay? Would be the same. And so let me just label it, would be positive 1 in this case. Okay, now how about fluorine? 7 valence electrons minus, you have 4 dots, 4 non-bonding electrons, minus half of its bonding electrons. Well, you have a double bond, therefore just multiply by 2, okay? And if you do the calculation, it's going to be, sorry, this is going to be 4, okay? So it's going to be positive 1, all right, positive 1, okay? Now, double check whether our calculation is correct or not. Negative 1, positive 1, positive 1, add those 3 together, you have positive 1. That is also matches with, with this charge of this ion, okay? So in theory, this is also a valid structure, but if you compare the two structures here, this one has 2 zeros, and this one has no 0, okay? According to rule number 3, smaller formal charge would be preferred. So that's why we say that, this one is not going to be very stable, even if it does exist, okay? The contribution of this structure to the real structure of this cation is negligible because it's not stable anyway. This one is the dominant, has a dominant contribution to the real structure. Okay, and again, if you do experiment, you will realize that indeed between the SO, it's a double bond. SF bond is a single bond. Okay, this is the fourth example. The last example here, CON minus. Well, now if you are talking about the CON minus, I would highly encourage you to draw the loose structures of this anion first, and you can pause this video, okay, and then try the loose structure. If I'll tell you that this one will have 3, okay, valid loose structures. Okay, you try your best and see if you can come up with the 3 resonance structures, 3 loose structures, and then you resume the video we'll work together. Okay. All right, folks, welcome back. All right, let me draw the 3 structures for you. Okay. Well, the first one, of course, carbon would be the central atom because it has the lowest electron negativity. Okay. Double bond, triple bond with nitrogen, single bond with oxygen. Okay. This is the first one. Second one, double bond with nitrogen and double bond with oxygen. Okay. And the third one, triple bond with oxygen, single bond with nitrogen. Okay. These are the 3 valid loose structure of this anion. Now, if you calculate the formal charge, okay, you can use the 2 rules to help us which one is the best. Okay, I'll label the formal charge on those 3 atoms directly, and you do the calculation of the formal charge by yourself. If you have any questions, you let me know. For this oxygen, -1. For this carbon, 0. For this nitrogen, 0. Again, if you check -1, 0, 0, you add them together, matches with the charge. The second structure, it's going to be 0, 0, -1. Okay. The third one would be -1, 0, -2. All right. So now it's time for us to decide which one is the best. Well, number 3 tells us if you have a smaller or more 0 formal charge, it's going to be preferred. This one, you have 2 zeros, 1 -1. 2, 0, 1, negative 1. Well, you have negative 1, negative 2, and 1, 0. So apparently that these two structures are better than this one. Okay. How about these two? They have the same number of zeros and same number of negative 1. All right, it's time for us to use number 4. Negative formal charge should reside on the most electronic negative atom. Here you can see that in this structure, nitrogen has a negative 1 formal charge. In this structure, oxygen has a negative 1 formal charge. We know that the oxygen has a higher electron negativity. Therefore, when you have negative formal charge on the atom with higher electron negativity, then this structure would be better than the others. Okay, so this structure has the greatest contribution to the real structure of this anion. Okay, this is going to be less, and this one, it's trivial. Okay, it's so small, and it can be ignored. All right. Again, please do practice, and if you have any questions, feel free to let me know.